Hi everyone and welcome back to PrepFusion. I am Anish and today we will start with the lecture 22 of our machines subject. So today we will discuss about three-phase transformers, and I know many students are daunted by this topic. Okay, they are very scared by this topic. Trust me, the way I will teach you, you will not be scared. And whatever is required for your exam point of view, we will follow that. Okay, because there are many things in three-phase transformer, but everything is not required. What is important? Only the connection diagram is important in the three-phase diagram or three-phase transformer. Only the connection, right? How are the each windings connected? That is important. Except that, like, that will be asked in your question. That's it. Okay, trust me, I will teach you systematically. If you follow me systematically, you will not ever face any problems while solving a three-phase transformer question. So before that, of course, we have done bit of basics on three phase connections configurations in the chapter 0. That's why it was there, right? Because it will be used later on. So I will just go through them, very small minute things, okay? Because we have already covered them there in the chapter 0. So three-phase transformer, three-phase configuration. First thing is, if unless and unless specified, your system will always be balanced. So your load also will be balanced, your supply also will be balanced, unless and until specified. Okay. A three-phase system connects voltage source to loads using either 3-wire or 4-wire transmission lines. These sources can be configured in the following configuration: Y or delta connection. Okay. So in Y connection, each phase voltage is measured from line terminal to neutral point, and in delta connection, each phases are connected in a loop, like here, right? They are in a loop basically. And in star, we have Y. Y is known as star. We have a neutral point. That is the difference between Y and delta connection. That's it. Okay. So I hope you remember that if I have three phases, then their phase difference will be 120 degrees. So each of the waveforms will be phase shifted by 120 degrees. Okay. So that was about the three-phase balanced three-phase system and balanced three-phase load. Now a few things we concluded in that lecture was that in case of star connection or Y connection, the voltages will be phase voltage, like first voltage VAN will be VP angle 0, VBN will be VP angle minus 120, then the C voltage will be VCN VP angle plus 120 degrees. Okay, so yeah, that is the case here. So these are my so this is the phase voltage, and the line voltage will be root 3 times this. Also one more thing, this we had derived that my line voltage in case of star connection, the line voltage leads the phase voltage by 30 degrees. So line voltage will lead the phase voltage by 30 degrees. That is what we know. Okay. This is my line voltage. So what is happening? There is a phase difference of plus 30. So line voltage will lead the phase voltage by 30 degrees, and it will be root 3 times Vp. It will be root 3 times Vp, and again it will lead by plus 30. Again it will lead by plus 30. This we had derived, okay, in the chapter 0. Same for delta. In case of delta, right? Like what is the phase current in case of star? Phase current and the line current are both same, because whatever current is coming here, this is known as the line current, and same is going through the phase. So in case of star connection, the phase current and line current will be same. But delta, it is just opposite. So in case of delta, the phase voltage and line voltage will be same. Okay. And what about the current? So the line current will be bit different than the phase current. Okay. So basically the phase current, right, will be this IAB, IP, IBC, IP, this, right? What will be the magnitude of the line current? So line current magnitude will be root 3 times the phase current magnitude. Okay. Also one more thing we have to keep in mind is that my line current lags. So this will be just the opposite, right? So line current lags the phase current by 30 degrees. Okay, this you have to keep in mind. Okay, these are the things that you have to keep in mind. Got it? So these are the mainly two things. One thing is this: the line voltage leads the phase voltage by 30 degrees. The line current lags the phase current by 30 degrees. Got it? So now let's start. Basically, let's start with the three-phase transformer. So how will I, now we have covered the basics of three-phase. Now let's start with the three-phase transformer. So there are many ways to solve a three-phase, like connect a three-phase supply, right, to transformers. One way is to use a transformer bank. What does transformer bank means? I have three phases. So what I will do, I will buy three single phase transformer. So it is not a single unit now. Okay, three different single phase transformer I will buy. That is known as transformer bank, and I will connect each phases. Right. So let's say this is neutral. So neutral will be connected with everything. So if I want if I want star connection, then let's say if I wanted star to star connection, right? Okay, or let's say if I wanted star to star connection. If I wanted star to star connection. So if I wanted star to star connection, that means what? That means basically that with everything the neutral will be connected, and this one also will be connected to the neutral. Okay, as it is a YY connection, this one also will be connected to the neutral. Okay, and each phase will be connected to each of the transformer. So phase A will be connected here, phase B will be connected here, and phase C will be connected here. That's it. Okay, so phase A, B, C, these are the connections basically. So now what about the other side? So delta means, sorry, star means basically the primary side will also be star connection and the secondary side also will be star connection. So let's assume that this phase is, let's say this is A, this is A dash, basically neutral, this is A, this is neutral again, this is B, this is neutral again, this is C. Okay, what about here? So here again the same thing, right? So this will be the capital A. Why capital A? Because assumption is, like I will tell you as well later on as we move along, that whenever I am writing capital, that means it is on the high voltage winding. So capital B, then on capital C. Okay, now we have this neutral connected here, neutral connected here, neutral connected here. A phase will be connected to A phase. Okay, B phase will be connected to B phase, and C phase will be connected, okay, sorry, to C phase. Okay, so that's how the connection is for a three phase transformer bank. It is not a single unit. Okay, very simple, very easy to understand. That's it. Three phase transformer bank is this only. So you might ask, sir, why don't we use this then? Like you have a three phase connection, we just have three transformer bank and we directly interconnect it. Why don't we use? So let's go through, we will understand why we don't use this. Okay, so in modern power systems, three phase generators are predominantly used to generate electrical power. So power generally is generated in three phase mode only. So there are three phase generator. Why in three phase? Because we can generate more power. That's why it is three phase. The power is then transmitted and distributed over three phase networks for efficient and balanced delivery. As such, a proper understanding of how this three phase transformers works is very important, because three phase transformers will be used in the three phase system. Okay, so there are mainly two kinds: three single phase transformers and a single three phase transformer unit. So this is a complete unit, and this is just a transformer bank, right? I have three transformers. So this picture, whatever you are seeing, this picture is of a three phase transformer. Okay, and this is a single unit. All these are single unit. So this is a core type three phase transformer, and this one is a shell type, right? So what you can observe, so actually what is the problem in this? Can you identify what is the problem here? So this here, right, this is totally a single phase, so both the LV and HV windings are present over here. Okay, both the LV and HV windings are present. LV and HV windings are present. Okay, both in a single limb only. So this will be, let's assume this will be phase A, this will be phase B, this will be phase C. Okay, now can you tell me what is the problem in this type of construction? The problem is the reluctance is different. If you see this winding, the flux will flow from here and here, right? And for this winding, the flux will flow from here and here. So actually it is not the same reluctance path. So what can be the problem? Problem can be, there can be bit of leakage reactors that will not go through the core. Okay, so here the problem in core type transformer is the reluctance is different. But here, right, if I see in this transformer, here all these are single unit transformer only. So in this transformer, the reluctance is same. As the reluctance is same, the flux distribution also will be same, right? Here the flux distribution might be bit different. Okay, so because there is insulation here, it is not like simple like some flux will flow through here. No, this flux will link like this will link like this will link like this. Okay, so in this type of transformer, the reluctance is same. Okay, that is what you need to understand. That is the only concept, right? Concept is reluctance is same. No need to memorize anything else. Okay, yeah. So we already know that in balance, like in three-phase winding, in balanced three-phase system, each winding currents, each winding carries currents that are equal in magnitude and 120-degree phase shifted. Okay, this balance condition ensures that the net magnetic flux in the transformer sums to 0. So what does it mean basically? That in a transformer, right, the I know that what are the sum of the currents? Sum of the current is IA, like for a simple star connected network, IA plus IB plus IC equals to 0, and I know IA is, let's assume I angle 0 plus I angle 120 plus I angle minus 120. Okay, this will be equals to 0. So from here what I can say is like all these currents also, like corresponding to this current, flux also will be phase shifted by 90 degrees. So flux will be phi, let's say phi angle 0 plus phi angle 120, like because the current and flux are proportional, so phi angle 120 plus phi angle minus 120. So what do we know? Like this is equals to 0. That means what? Basically in the core, right, the same sinusoidal flux is flowing and the three fluxes are 120-degree phase apart. So if the three fluxes are 120-degree phase apart, that means the average flux at a cycle, in a cycle, the average flux in a cycle will be 0. Okay, you can take the integration, you will see the flux contributed by phase A, the flux contributed by phase B, the flux contributed by phase C. If I take out the average in a particular section, it will be 0. That helps in what? Minimizing the vibrations and noise in the transformer. That would not happen possible in a single phase transformer. So a single unit three phase transformer has this advantage. So this is the advantage of a single unit advantage of a single unit three phase transformer. Okay, like 3-unit single phase transformer has this advantage that I can just simply connect these two wires and that's it. But they might have noise, they might have vibrations. So those things can be mitigated in a single unit 3-phase transformer. But somehow if this gets damaged, everything is damaged. But here, even if one of them gets damaged, the other two phase will be totally intact. So here the differences are written here actually. So construction, like for the three-phase transformer, single unit with a common magnetic core. For the three-phase transformer bank, three separate single-phase units. Cost will be higher due to more iron insulation and bushings and design procedure, because it is a single unit only. I have to think about everything. How will I place the three phases? How will the flux flow? All those things extra I have to implement. R&D I have to do. So for that, the cost will be higher to develop a single unit three-phase transformer. To develop a three-phase transformer bank, the cost will be lower and the design will be very simpler. Okay, so floor space, of course it will require less floor space because it's a single unit, right? I am building a single unit in a same unit structure, right? So it will require less space, it will require more space. Three-phase transformer bank will require more space. Okay, so then we have installation flexibility. It is less flexible because, like, I cannot simply change the windings, I cannot change the code that easily, but here it is more flexible, right? I can configure externally here, right? Once the connection is fixed, like if it's a star delta transformer, once the connection is fixed, then I cannot change it outside, right? But as you can see that in a simple transformer bank, that if I want to configure it star delta, it depends on how I want to connect this wires, right? That's it, the external wires. Okay, externally we can change it, but here the wiring is done internally, so I cannot change internally. Maintenance, if one winding fails, the entire transformer will be affected, like because they have a common magnetic path. If one unit fails, only that unit will be replaced, just like parallel operation of transformer. It is full three-phase unit needed as pair, only one unit single phase unit need. Okay, efficiency will be lower due to higher iron loss. Yeah, I guess this is wrong actually. Higher due to lesser core volume. No, this is wrong, right? Efficiency will be higher here actually. Wrong. This point should be here. So here, because it's a single core, right, and flux path is same, so efficiency here will be higher in case of a single unit transformer, and here it will be lower. Okay, so here it will be higher efficiency, here it will be lower efficiency. The reason I have already explained, because like I'm using three different single phase transformers. Okay, just simply me. So although single phase transformers has also good efficiency, but if it's a single unit, right, I will think about everything, so I will make it more efficient. Okay, because the core is same, so magnetic flux path will see less reluctance. Harmonics, like there are harmonics here, we will discuss about this later on. Okay, uh, yeah, these are the few differences you can go through. Now let's like discuss a three-phase transformer bank and how can I make a three-phase transformer bank together. Okay, how can I make it? So a three-phase transformer bank is like, how can I like diagrammatically show it? Okay, if I want to build a single code, like this is one of the way which I can develop a three-phase transformer bank. There is another way. Just connect all these three, right, together. That's it. Just connect all these three together, and now you will understand how will the flux distribution be. Flux distribution will not be even. Okay, I will show you. So basically what we do is we have this core over here. In this core I have, like, okay, it is already made, so that is known as the cell type transformer. We will discuss about that. So okay, it is already there right here. So here it is. So what we do is we have, it is a cell type transformer. Okay, it is a single unit cell type transformer, not single unit, sorry, transformer bank cell type transformer, because it is simply there are three cores here, three legs here, that's it. Okay, now what is the problem here? The problem here will be the flux distribution will not be same. How? Why? So if I have a phase here, so let's assume that the A phase is developing a flux of phi A. So if the A phase is developing a flux of phi A, okay, A phase is developing a flux of phi A, then from here, right, I will see two parts. So phi A by 2 will go here, and phi A by 2 will come here. Okay, I'll see two parts. Same for this one as well, right? Same for the phase B. So from phase B again, this flux will come phi b, phi b by 2 will come here, phi b by 2 will come here. So there is a problem. I will explain what is the problem. And same for here as well. Phi c will come. So phi c by 2 will go here and phi c by 2 will go here. What is the problem? So the problem is like from here, basically from here phi b by 2 will go, and from here phi b by 2 will go. Okay. And same for here as well, right? Phi b by 2. So if you observe one thing, that near here the flux is more and here the flux is lower, like because these two flux sometimes subtraction is happening, I don't know exactly the value, but flux will be lower, right? Or flux value will be different, right? Here flux value will be different, here flux value is definitely different. It is only phi b, here it is something else. I will calculate that value as well, don't worry. Okay, so what is the problem? So if the flux here it's, let's say, phi b, and what is the flux here? Let's assume any at this place, right? Let's assume this place only, or let's assume with respect to phi a. So if I see phi a value will be coming from here, phi a by 2 coming from here, phi a by 2. So this value here, what is the flux? Here the flux is phi a by 2 minus phi b by 2. Okay, and remember I told you that all these are phasor quantities, right? Because IA will produce a flux phi a, and these are all balanced flux. IB will produce a flux phi b, and IC will produce a flux phi c. Okay, so all these are balanced flux. That means these are also balanced. So phi a will be, let's assume, a phi m angle 0, phi b will be phi m angle 120, and phi c will be phi m angle minus 120. Okay, so what is this value? It is phi a minus phi b by 2. So phi a minus phi b by 2. So basically it is in phasor, it is phi m angle 0 minus phi m angle 120 degrees divided by 2. Okay, so I can simply solve this, right? I can very easily solve this. So it will be what? So if I want to solve this, okay, you can break it down, right? So this will be what? If I break it down into two real and imaginary portions, so this will be phi m angle 0 only. So this will be phi m only. Okay, I need another page. So this value will be phi m only, then minus, this is phi m cos of 120. Cos of 120 will be minus of, I guess, yes. So this will be minus of phi m by 2, then plus sine of 120. Sine of 120 is 0.866. So j root 3 by 2 phi m divided by 2. Okay, so this value comes out to be 3 by 2. So 2 I can take common, right? So this will be 1 by 2 I can take common. So this will be phi m 3 phi m plus j root 3 phi m. Phi m also I can take common, right? Root 3 also I can take common. Okay, I can take a lot of things common. So root 3 if I take common, root 3 phi m if I take common, this will be root 3 plus j only. Okay, and now if I want to like, this is the resultant phi m where here, resultant phi m here. So not phi m, sorry, resultant flux at this particular location. So resultant flux at this particular location is this value. So that is equals to, if I want to calculate the magnitude of the resultant flux, this value will be what? This value will be root 3 by 4 phi m, 3 square plus 1 square whole under root. So root 3 square plus 1 square whole under root, that is 2. So this will come out to be root 3 by 2. So the magnitude here is root 3 by 2 phi m. So here the magnitude is root 3 by 2 phi m, like in this region, in this region, in this region, in this region, in this region. And here what is the magnitude? Phi m. Here it is the magnitude phi m, because it is equals to phi b only, and magnitude of phi b is phi m only. Here also same. So here it is 0.866 phi m. So the in different regions the flux is different. If the flux, maximum flux is different, and I know the core is same, right? It is made of same material. So the maximum flux density Bm is same, right? Maximum flux density a core can support is same. So what I have to do? I want my Bm to be same. Maximum flux density at every point I want it to be same, right? What is Bm equals to? Bm is equals to flux by area. Okay, so I can say that my flux is changing. If flux is changing, then my area also has to change. So that's why, as in the legs here, right, in this region the flux is smaller. So if flux is smaller, the area also will be smaller. And in this region flux is larger, it is phi m, magnitude peak flux is phi m. So here area also will be larger. So here, like, this can be interview question. Okay, why is the area smaller here? Although visually it seems like area here is bigger, no, area here is not bigger. So because like both flux are going, right, that is why. Because here also the area is again small, right? How much flux is going here? Again phi c by 2, here again phi c by 2, correct? It is even smaller. So if you want to conclude everything, that as the maximum flux is changing, hence the area will change as maximum flux changes. Okay, okay, so now let's like, this was the problem with this cell type transformer. Okay, that is the problem, right? Because we cannot make the area same, because if I make the area same, what will happen? If I make the area same, let's say area is A only, in some region the flux will be phi m, some region it will be 0.866 phi m. So if my Bm is fixed, right, and if my area is fixed, flux is different. So in some regions the core may get saturated. So here, as flux is changing, core may saturate. Okay, so that's why we have to change the area. We cannot keep the area same. Same thing is written over here. The central limb offers lower reluctance than the side limb. As a result, flux produced in the side limbs does not split equally, whereas flux in the central limbs divide equally for a core type transformer. So this is the core type transformer, right? This was the core type transformer. So in the central limb, right, the flux, because from here, whatever, let's say here phase B is there, so we'll copy this thing. Okay, so this is a core type transformer, and I will paste this here. So this we are talking about the core type transformer, the first lecture. So this right here, if I have phase B here if I have phase A, here if I have phase C. Okay, so if I have phase ABC, so from here, right, the flux is getting distributed equally. There is no problem with that. So because it will see from left hand side also same reluctance, right hand side also same reluctance, correct? So here also this phi b by 2 will go, here also phi b by 2 will go, but the phase A will not see reluctance equally. So some flux will flow here, some flux will flow through here. That is not equal, like that will not equally be divided. So there is a problem. Due to that, there can be leakage flux, more leakage flux. That is the problem for a co-type transformer. So this was the problem for a co-type transformer. All this will be asked in interviews. That's why I am explaining you. For exam point of view, gate point of view, not that important. Okay, so that's why the flux distribution in co-type transformer is not perfectly uniform due to asymmetry in the magnetic path. What is the problem in cell type transformer? So in cell type transformer, the magnetic flux is confined more efficiently by surrounding it with iron on both sides. So both sides, if I see cell type transformer, both sides are iron. Okay, everywhere it is surrounded by iron only. Okay, but what is the problem for a cell type transformer? The problem for a cell type transformer is the central limb carries all the windings. So here it carries all the windings, while the outer limbs carries only the returning flux. So these limbs only carry the returning flux. The central limb carries the windings. Okay, since the magnetic flux is maintained nearly constant, the cross sectional area of the outer limbs is often made half, because here half of the flux is going, right? If you see here, phi a by 2 is flowing in the outer limbs. Here also phi c by 2 will go. Phi c by 2 will go. Okay, so as half of the flux is going, that's why the area will be half here. That's why visually also you can understand the area is half here, right? Area will be thickest here, and area will be slightly thinner than this one here. Okay, so yeah, cell type transformers ensure better magnetic coupling and are more magnetically robust. Okay, so it is better than the co-type transformer, but it will support better magnetic coupling, because although like this flux is dividing equally, getting divided equally, but the construction is a problem, right? Making it is a problem. So here the area is different, here the area is different, here the area is different. So constructionally there is a bit of challenge. Okay, so these are the difference between cell type and co-type. You can go through this, I will not go through this. Okay, these are just for interview purpose. So now let's come to the main topic that we actually want to discuss. Okay, three-phase transformer configurations. So of course, you know that mainly in three phase there are two types of connections: star connection, delta connection. Okay, star connection and delta connection. We will decode every single thing. If the high voltage winding is star, low voltage winding is delta. If the high voltage winding is delta, low voltage winding is star. Every single thing will be decoded crystal clearly. Okay, so three phase transformers are extremely used in this all areas. So first we will discuss about few notations of three phase transformers. So what are the notations? Basically, whenever we have written star and it is in capital, like Y, capital D, capital Z, Z is for zigzag. We will discuss about that. That means that it represents the high voltage winding. So if Y is in capital, if Y is in capital, that means it will be high voltage winding, D capital, Z capital. Okay. If it is in small, let's say small y, small d, small z, then it will be the low voltage winding. Okay, it represents the low voltage winding. So this is the first notation. So how can I define this transformer star delta? If high voltage winding is the star and low voltage winding is the delta, that means I will write here, this will be Y and this will be D. That's how I will define a star delta transformer with its high voltage winding as star and low voltage winding as delta. Same thing here. If the low voltage winding is now star and high voltage winding is delta, how will I define? So the low voltage winding will be delta, that is low voltage winding will be star now, so it will be small y, and the high voltage winding will be delta, so it will be capital D. So that's how I write the transformer notations. If I know, so we write the capital letter first, so dy will be the correct notation. Y, not yd, dy will be the correct notation. Okay, so that's how we write basically the notations and transformer configurations. Okay, I hope you have understood this basic point. Now let's come to one more point. Okay, let's now come to one more point. So here I have these two coils of a single phase transformer. Very simple, right? Single phase transformer. Let's say this is phase A, phase B. So if A1, A2 is capital, so this is capital, right? If these are capital, that means what? These represent that these are high voltage winding. If these are small, that means what? This represents these are low voltage winding. Okay, so these are high voltage winding if these are capital, and if these are low voltage, if these are like small letters, this will be low voltage winding. Got it? Okay, so that is one more thing that you need to keep in mind. One more thing is, if like it will be mentioned that you will see if it is like mentioned 1 is with dot, or if any one of the coil has dot with A1, with the terminal A1, that means with all the other terminals as well, with the 1 there will be dot. So if 1 is with dot, and let's assume that this is A1, right? So let's assume that I draw my transformer, like I draw the windings of my transformer. So if they're telling you that 1 is with dot, so everywhere else 1 will be with dot. What do I mean by it? So if let's say I have a star delta transformer, okay, or any winding, you will just draw the 3 phase windings. So this is the A1 A2, this is the B1 B2, and this is the C1 C2. Okay, so now now if I know that 1 is with dot, if any one of the winding I see a dot with 1, that means with all the rest of the windings also 1 will be present with dot only. And if in the low voltage winding as well, 1 will be present with dot only. Okay, don't confuse with yourself, 1 will be present with dot only. So low voltage winding also I will draw. So let's I am running out of colors, so let's say this is my, I have yet to connect the low voltage windings. How are they connected? I will discuss about that. Okay, so this is, let's assume this is A1 A2, let's assume this is B1 B2, and this is C1 C2. Okay, okay, what happened? This got locked, I guess. Yes. Okay, this also is locked down. So here also 1 will be with the dot, so 1 will be with the dot. Now if 2 is with the dot, if 2 is with the dot, it's very simple again. I'll just change this to here, we are running out of space. If 2 is with the dot, I will just copy this thing, then everywhere else my dot will be connected to the second terminal here. That is the only difference, right? We are just learning how to draw the transformer coils. We will slowly understand every single thing. Now let's understand the clock notation. What do I mean by clock notation? Clock notation. Okay, what do I mean by clock notation? So what is clock notation basically? So clock notation is basically tells me that what is the phase difference between the high voltage and the low voltage winding. Okay, so this tells me the phase difference between HV and LV winding. HV line voltages, HV and LV line voltages. Okay, so now what I can say is that how can I find out the phase difference? What do I know? I know that this is what kind of transformer. Can you tell me, identify what kind of transformer is this? Like what kind of connection is this? I see all the 3 points are shorted together. When are all the 3 points shorted? If you see, right, if you see here in the first case. So why, right, everywhere these 3 points are shorted. What are these 3 points? Neutral. So where is neutral present? Star connection. Also from here also you can understand, like I will draw it here as well. I forgot to write, I forgot to take this delta and star. Yeah, I will take this circuit actually, this way you will understand better. So how do I identify whether it is a star or it is a delta? So you can simply identify like this. Okay, we'll see. So here, right, basically it will be let's assume like my here 2 is with dot, right, 2 is with dot. So if my assumption is 2 is with dot, so this will be, let's assume these are high voltage winding A1 A2. Okay, 2 is with dot, right. Okay, let's assume here 1 is with dot actually. Oh no, okay, let's keep it, let's here I assume 1 is with dot. So if 1 is with dot, that means this will be A1 A2, this will be B1 B2, and this will be C2 C1. So I see that B2 C2 and A2, all these three terminals are shorted together at this point for a star network, right? And A1 C1 B1 are all connected differently. Here as well same thing, right? Just the number is opposite. Okay, so A2 B2 C2 are all sorted together, and A1 B1 C1 are all separate. Okay, A1 B1 C1 are all separate, correct? So what kind of connection is this? Star connection. This is a star connection. Okay, now whenever you see that here, right, again the same thing, one is with dot. So here this will be B1, change the color, B1 B2, this will be C1 C2, this will be let's assume this will be A1 A2. So whenever I see that like numbering is different, B1 is shorted with A2, A1 is shorted with C2, or C1 is shorted with B2, so numbering is different, right? The phase is different and the number is different. That means what? That means it is a delta connection. So this is a delta connection. So this kind of connection is a delta connection. So if we see here that C2 and A1 are connected, then again phase changes, A2 and B1 are connected, and B2 and C1 are connected. So this is a delta connection. So from this connection diagram, I can at least identify that it is a what? It is a star delta transformer, because A is the capital term, so that means star side is the high voltage side, so it will be capital Y D transformer. Now how do I identify the phase difference? Okay, how do I identify the phase difference? So if I assume that the line voltage is at 0 degree, okay, line voltage of this high voltage side is at 0 degree, then what will the phase voltage be? I know for a star connection the line voltage leads the phase voltage by 30 degrees. So here, right, basically I can directly write that the phase voltage, the phase voltage will lag the line voltage by 30 degrees. So here if VAB was V angle 0, this will be magnitude will be V by root 3 angle minus 30 degrees. Okay, and I know like here, right, there is actually here there is no phase difference. So from here to here there is no phase difference. So we will discuss about that, don't worry, we will discuss about that. Okay, in delta what happens? In delta the line voltage and phase voltage are same, so this phase is same copied here. I will discuss about this, don't worry, because from this point to this point there is actually no phase difference. Okay, I will discuss, don't worry, I will discuss about this. So here the phase is again v by root 3 minus 30 and line voltage is again v by root 3 minus 30. So what I can comment? I can comment that here the line voltage is what? Here the line voltage is v by root 3 minus 30. There is trans ratio, I'm ignoring it, I'm just considering the phase difference. I just want to focus on the phase difference right now. Okay, just want to focus on the phase difference. So what is the phase of the line voltage? That is minus 30. So I can see my line voltage of the high voltage winding was 0 degrees and line voltage of the low voltage winding is minus 30. So the low voltage winding will lag the high voltage winding by 30 degrees. Okay, so I can safely say that here, right, my theta will be 30 degrees. Why? This is my generally the high voltage line, like line voltage of the high voltage winding is the reference, that is at 12 o'clock. Okay, and this will lie in the 1 o'clock because it is lagging, hence it is in the clockwise direction with respect to high voltage winding. So angle is always calculated with respect to the high voltage winding. As it is lagging, that's why it is in the clockwise direction. Okay, that's why it is in the clockwise direction as it is lagging. Got it? And why is it in the 1 o'clock? Because it is lagging it by 30 degrees, and I know this whole circle is 360 degrees. So 360 degrees divided by the number of hours, that is 12. So this will give me 30 degrees. Okay, so basically 1 hour will be 30 degrees, this we already know. So here it will just lag by 30 degrees, that's it. Okay, so this is basically the clock notation. We will solve others as well, don't worry, we will solve. I will give you questions, I want you to try it out and we'll come back to that. So what is the clock? So HV side is always assumed to be at 12 o'clock, that is a reference position. The LV winding phase shift is then described in terms of clock hour position. So LV side, right, will be described by the clock hour. So either there it will be a multiple of 30 degrees. So that's why it will be either in 1 o'clock, 11 o'clock. So what is the connection name here? Actually, it is not only YD. So YD does not tell me complete information about this transformer. The name of this transformer will be YD1. Why YD1? YD1 tells me that the phase difference between the primary side, high voltage side line voltage, and the low voltage side line winding is like the low voltage winding will be at the 1 o'clock. So 1 o'clock means 30 degree phase difference, that is lag 30 degree. Okay, so that only this information will tell. Okay, that is what is written over here. Positive phase shift means LV voltage lags the, sorry, positive phase shift, actually, yeah, positive phase shift means LV voltage lags the HV. Actually no, right, here negative phase shift is there only. No, negative phase shift means, negative phase shift only means LV lags the HV voltage, sorry. So sorry, this will be negative, this will not be positive, actually it will be negative only. So this will be negative only. Okay, this will be negative and this will be positive. So negative phase shift means LV lags, and negative means I will go in the clockwise direction. This we already know, right? Negative means I will go in the clockwise direction, positive means I will go in the anti-clockwise direction according to graph. Okay, according to simple graph. So here there was a bit of mistake on my behalf. So this will be negative 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 is here, and this is positive. Okay, so this is negative phase shift, this is positive phase shift, and yeah. So why negative? Negative means, always remember, negative means I will move in the clockwise direction, and positive means I will move in the anti-clockwise direction. So basically what will move in the clockwise direction? My low voltage winding, that is the our hand, right, or the like small hand. Basically high voltage is represented by the larger hand and low voltage is represented by the smaller hand. Okay, so I hope you have got this point. Now with this basic concept, okay, with this basic concept only, with this basic concept that the voltage difference between the line and the phase for a star connection is 30 degrees lag or lead depending on from where you are taking the reference. For a delta it is same, there is no voltage difference. From this concept can you identify the transformer configurations? Pause the video and try to identify the following transformer configurations. Okay, so let's start with this, right? So here basically I will actually not draw the configurations now. Just by seeing the clock diagram and just by seeing the connections can I identify what kind of transformer is this. Okay, I will not derive the expression right now. I will not connect the wires and derive the expression. No, not doing that right now. Okay, so if this clock diagram is given, okay, this means what? The HV winding is leading the LV winding. Sorry, the LV winding is leading the HV winding. So there is a phase difference of 30 degrees. So the option A, first of all, I will identify HV winding is what? HV winding is star connected. So it will be Y. What is LV winding? LV winding is delta connected. So it will be D. Now, where is the LV winding located? So I am just teaching you how can you write down the expressions. Of course, we will derive each of these transformers. How is the phase difference? All those things we will derive. Don't worry about it. So this will be YD11. Why? Because the LV winding is in the 11 o'clock. So it will be YD11. Okay. So basically what I can comment is that if it is YD11, that means the LV winding, LV like voltage of LV winding, line voltage of LV winding leads the phase voltage of HV, sorry, not phase, sorry, line voltage of HV winding. Okay. Then what about the B, part B? So part B, if I see, this is basically same, right? They are in same phase. So again, the high voltage is star, low voltage is also star. So it is star star. Okay. And star star we generally don't write here 0. For star star it is just star star only, YY only. We generally don't write here 0. Okay, star star we generally don't write 0. It is YY only. Generally you can write 0 as well, that is fine, but we generally ignore. By default we assume it is star star 0 only. So sorry, this is small, right? Because the low voltage side is the star, high voltage side is star. So Y will be large, Y0 will be small. Okay, yeah. So what about the other portion? What about this? So here again there is no phase difference between the line voltage of the LV winding and line voltage of the phase, HV winding. Okay. What about the C? Just I am telling you how can I write down the transformer notation. That's it, specification. So here if I see the line, high voltage side is star, low voltage side is star. So again it is star star only. So YY only. Okay, and it is here it is phase opposition, right? So it is in 6 o'clock. So it will be YY6. So here what I can comment that the line voltage in the LV winding and the line voltage in the HV winding, there is a phase difference of 180 degrees. So you can either write lag or lead, because if I go 180 clockwise or 180 anti-clockwise, it's the same thing. Okay, it's the same thing. So I can write here lag or lead. Lag or lead. Lead the line voltage of HV winding by 180 degrees. Previously it was actually 30 degrees. I forgot to write there the amount of degrees, right? Here it is by 30 degrees. Okay, got it? So these are the three notations. So just we want to identify the configuration. How can I get back the configurations? I have not yet discussed how is the phase difference calculated. Those things I have yet to discuss. Okay, don't worry, I will discuss about those. Okay, so Yeah, let's now come to this phase shift consideration. So phase shift in three phase transformers is always reference to line voltage. As I have discussed, we will always see line to line voltage with with respect to which I will compare the phase difference. I will never see phase. I will never compare the phase voltages. I will never compare the phase voltages. Okay, I will never ever compare the phase voltages. Okay, this is critical in parallel operation of different transformer units. Phase voltages, phase alignment must be maintained to avoid circulating currents. So previously, right, you remember, if there is phase difference, then there will be circulating currents. Why? If phase alignment is not there, what do I mean by phase alignment? So let's say I have two transformers. One is this YD1, another one is YD11. Okay, YD1 and YD11. So if I have two transformers, that means what? That means what I can comment is this will provide a phase shift of around what the LV winding will lag. So 30-degree lag, LV winding will lag, and here it will be 30-degree lead. LV winding will lead. So what will be the problem? I can explain. So let me come to the, let's assume that the LV winding is the secondary side. So if I draw the secondary side, and if these two transformers are connected in parallel, so this voltage source will be some of angle minus 30. Okay, and this voltage source will be some of angle plus 30. Although the voltage magnitude is same, because like turns ratio is same, that's why they are connected in parallel. Voltage ratings also will be same, but so this is, let's assume this is transformer A ZA, and let's assume this is transformer B ZB. I'm just drawing the single phase equivalent. Okay, it will be three phase, but I'm just drawing the single phase equivalent ZB. So, and this is the load basically. Here I will have the load, right? This will be the load basically. What will be the problem here? Although the magnitudes are same, as the phase is different, right? You can calculate there will be a circulating current. Again, we hate circulating current, right? We don't want current to circulate. That will just damage the core, because my core is not rated for this extra current. Whatever we have calculated, we have just only calculated for the load current. We have not considered the circulating current that will flow in the core. Very bad thing, right? That's why phase alignment is very important. That's why they must be of same configuration. Otherwise, there will be this problem. Okay. Okay, terminals with identical numbering on HV and LV side denote the same voltage polarity. I will discuss about this. What do I mean by same voltage polarity? So there will not be any phase difference between the coils. Very important. There will not be any phase difference between the coils. There will not be any phase difference between the coils. Okay. Dot convention is often used. Dot convention is often used to indicate instantaneous polarity. That we have already discussed. We already know. And if dots are provided, numbering should match to preserve polarity. What does it mean? If I see that if one of the coils has dot connected to one, that means all the other coils also should follow the same numbering. If I see in this whole diagram that in one of the coils dot is connected to 1, in the other coil dot is connected to 2, that means something is wrong with the circuit diagram. Circuit diagram is not correct. Circuit diagram is invalid. So numbering must match. This whatever scheme I will follow must match and preserve, right, the polarity. Okay. So now how did this came here? Okay, this is a question basically. So before that, actually, okay, I will start with star connection. Is it there already? Yeah, star connection is later. Okay, this is the question that I will solve first. Okay, so there are two 3-limb 3-phase transformers with delta star connection are supplied from the same source. One transformer is DY1 connection, other one is DY11. What is the phase difference between the corresponding secondary phase voltages of these two transformers? Can you say what will be the phase difference? Very easy, right? One is DY1, other one is DY11. So we have already discussed. So one is DY1, other one is DY11. So what is the phase difference between the secondary voltages, right? They're asking us between the corresponding secondary phase voltages. So one will lead by 30 degree, other will lag by 30 degree. So what will be the overall phase difference? Overall phase difference will be 60 degrees. Correct? Okay. Whatever, I don't care. Overall phase difference between the voltages will be 60 degrees. Correct? So dy1 will provide a phase difference between the line to line voltage from HV to LV it will provide a phase difference of minus 30 degrees lag, and dy11 will provide a phase lead of plus 30 degrees. Okay, so what will be the overall phase difference between the secondary voltages? It will be, overall phase difference will be 30 minus of 30, so it will be minus of 60 degrees. So this is my overall phase difference, or like they have asked me magnitude, so 60 degrees will be that phase difference, minus or plus does not matter. So this is my overall phase difference, between the secondary voltages. So without even explaining anything, we were able to solve a very basic and simple question. Okay, so in three phase, right, mostly this basic questions will come, not very difficult. So overall phase difference will be 60 degrees. This will be the phase difference. Okay, now actually let's come to the connections. Let's actually understand the connections. So first I will discuss about star-star connection. Okay, I will discuss about star-star connection. What is this 1:x? Everything I will come to. I will come to every single thing. Okay, so in star-star connection, let's first discuss y0. Okay, let's first discuss y0. So y0 or y, basically, what does it mean? It basically means that both windings are star connected. If both windings are star connected, that means either this all A2 will be shorted, or all the two terminals will be shorted, or all the one terminals will be shorted. But I am observing that I am giving phase input to A, B and C here in the one terminal, so I cannot short this. Of course, I will short the other one. So here other one will be shorted to make it star connection, and here as well I am taking the outputs from the terminal 1, so other one, that is A2, B2 and C2 will be shorted. Okay, A2, B2, C2 will be shorted. Got it? So now what is the other thing? Other thing is basically, that that what I can say is that, how do I find out the phase difference now? So one thing you should always keep in mind, that these are my phase voltages, VA, VB, VC. Okay, in the coil, in the primary. So I have drawn, so they will be it is a balanced load, so they will be phased apart by 120 degrees. So please keep in mind that there will not be any phase shift between primary and secondary. Between the coils of the primary and coils of the secondary, there will not be any phase shift. Got it? There will not be any phase shift between the coils of the primary and coils of the secondary. Okay, got it? So basically this VA, VB, VC will be copied here exactly for the low voltage winding. For the phase, okay, we delete this, for the phase voltages. So for the phase voltages, okay, VA, VB, VC. So there actually will never be a phase difference. What will be there? So basically this X, right? This X represents the transformation ratio between the primary winding to the secondary winding. So these are windings. These are all called phase windings. So actually here, what will be my VA? So this is the ratio, basically turns ratio. So my capital VA by small VA will give me the turns ratio, that is 1 by X. So my small VA will be basically X into VA. That's it. So it is basically transformation ratio. That's why VA and small VA and capital VA are both in phase. I have not discussed about line voltage. I have only discussed about phase voltages in the transformer. So not even phase voltages, the coil voltages. So these are called as the coil voltages. Okay, as you might get confused with the terms, so I will call these as coil voltages. Okay, these are called coil voltages, right? So coil voltages, you see that it will be derived from this transformation ratio only, like turns ratio only. Okay, so this VA will be X into VA. So there is no phase difference, For now we can see there is no phase difference between the coil voltages, no phase difference. Okay, there is no phase difference between the coil voltages. So what will be the line voltage, what will be the phase difference between the line voltage? So if I draw the phase difference of the high voltage winding, sorry, no, what will be the line voltage of the high voltage winding? So line voltage will be this VA minus VB, right? Let me just draw one of the line voltage, VAV. So it will be VA minus VB, so it will be somewhere here, correct? This will be my minus of V, and I will add these two. So if I add these two, this will be this value. Okay, so that is VAV. And in the low voltage side as well, if I write here this as my minus of VB, and this as my V only. So if I add this, I am observing what is the, can you observe the phase difference now between the primary, between the line voltage of the HV winding and the line voltage of the LV winding? Can you say me what is the phase difference between these two? The phase difference is very simple, right? It is simply 0 degrees, because both are exactly like phase is exactly same. So this is small VAB. So I see there is no phase difference between line HV and LV side, line LV side. Literally there is no phase difference. So if there is no phase difference, then it will be very easy for us, right? So like what will be the clock diagram? Clock diagram, I hope you can draw. So clock diagram we will draw. Clock diagram will be something, okay, I have to copy the clock, right? So if I copy, this will be the clock diagram, basically this, as there is no phase difference, that is what we derive, right? So this is the exact connection. Okay, when will there be phase difference? I will discuss, don't worry, I will discuss when will there be phase difference as well. Okay, so this will be the clock diagram basically. Okay, so that's how you find out the phase difference. When will there be phase difference? I will discuss. Now one more thing, what is the transformation ratio of the primary and secondary line voltages? Because this was only for the coil voltages, this was for the coil voltage. In this case, the coil voltage and the phase voltage both are same. So first point to note here is, in star connection, the coil voltage equals to phase voltage. Coil voltage equals to phase voltage. Okay, point 1. Point 2 is, I know the phase voltage difference. So basically I can say that phase A, voltage of phase A divided by capital A, it will be X basically, correct? 1 is to X, so it is X only. What about line voltages? So what is my line voltage VAB, capital AB? It will be root 3 magnitude. I am only discussing about magnitude. Phase we had already discussed. So I am only talking about magnitude. So it will be root VAB will be equals to root 3 into VA. Okay, and root small VAB. So this will be capital A, right? And this will be root 3 into small VA. Okay, so I can directly say here that I can replace VA. So what will be capital VA? So what will be VA capital? It will be magnitude of VAB divided by root 3. Okay, so and here also same, right? So basically what is happening here is that this will be small VA will be replaced with VAB magnitude divided by root 3, and this will be replaced with VAB magnitude divided by root 3. Okay, so this will be equals to x. So from here the ratio of line voltages, so the ratio of the line voltages I can find out. So ratio of line voltages will be magnitude of VAB is same intact as the coil voltages, that is magnitude of capital VAB by x. Okay, so do we need to remember this? I hope you can derive this, right? It will not take you, it will hardly take you 20 seconds. So I mean automatically anyways it will be in your brain, but it should not take you more than this to remember this, right? For star star connection this does not change, the line voltage and the phase voltage does not change for star star connection. For delta star these things will change as we move along. Okay, so I hope you have understood this basic point. Now there are two cases, this was the case 1. Okay, now let's discuss about the case 2. Case 2 is when my phase difference is y by 6. So if my phase difference is y by 6, how will the windings be connected? So this time, right, instead of connecting all the non-dots, what I did, in the primary side, in the high voltage side, I connected all the non-dots, which are not dots, and in the low voltage side, I connected all the dots. So it developed a phase difference of 180 degrees. So it developed a phase difference of 180 degrees. How? I will explain with the winding diagram. I will explain with the winding diagram. So here if you see, I am developing a voltage of VA, I am developing a voltage of VV. Okay, VA, VV, VC. So if I write here, this is plus, this is minus, right? Instantaneous polarity. Instantaneous polarity. This is plus, this is minus. This is plus, this is minus. So phase voltages will never go out of sense. Phase voltages will always be same. So here if I write my, what is my VAB? If I write what is my VAB, so my VAB will be what? If I apply a KVL basically, or you can directly write VAB will be this VA minus of VB, correct? Because this is plus, this is minus. Okay, so my VAB will be VA minus of VB. Okay, what about here? Same thing, right? Again this is plus because this is dot, this is minus, this is plus, this is minus. So here again the same thing, that my, what is my VAB? VAB is VA minus VB. Okay, so VAB is VA minus VB, same thing. Okay, but what about the other side? And remember this capital VA and small va are always in the same phase. This capital VA and small va will always be in the same phase. There will not be any phase difference between capital VA and small va, same as capital VB and small vb. Okay, there will never be any phase difference, remember that. So let's now come to the next type of connection, which is y by 6. So in y by 6 it will just be the opposite of y by 0. What does y by 6 means? Y by 6 means I will have a phase difference of 180 degrees. So there will be a phase difference of 180 degrees from the high voltage side to low voltage, from the HV side to LV. HV to LV. Okay, the phase difference will be from high voltage to low voltage will be 180 degrees. Okay, so now how is it possible? So what previously what we did was we had connected all the non-dots together, right, in the high voltage and in the low voltage winding. But here what we will do, we will connect all like this side, the high voltage side I will connect the non-dots, but in the low voltage side I will connect the dots. What difference it will make? The difference it will make is that phase difference will be 180. How? I will show you. Just remember this, that the coil voltages will not have any phase difference. Coil voltage of the phase A, coil voltage of the phase in the low voltage side and the high voltage side, there is 0 degree phase difference between the coil voltages. Okay, there is 0 degree phase difference between the coil voltages. So this is also 120 degrees, right? Okay, now let's calculate why is there a difference of 180 degrees. Okay, so first thing is, let us discuss about the magnitude, like what will be the line voltage magnitude. So again same thing, right? If I see here, VA and VA will be same, but what is the line voltage here? Here what is the line voltage? So the line voltage VAB will be what? VAB in the high voltage side will be equals to VA minus VB, right? Simple, like this is plus first, like this will be plus VA minus VB. Okay, now what will be my V small ab? So if we see V small ab, right, if you observe that here I have a negative sign. Why? Because dot is with plus, non-dot will be minus. So this is negative, this is plus. Now it is opposite polarity. So V small ab V small ab will be equals to V small a minus V small b. Okay, now not will it be this? No, this will not be this, right? It will be actually opposite, because negative sign is first, right? So this will be minus VA plus VB. What is it? It is basically minus of VA minus VB. So previously whatever we had calculated, that was VA minus VB, VAB was supposed to be VA minus VB, right? Previously we had calculated. Now it is negative of this. So basically, right, it will be just the opposite. Here VA minus VB is same, but small VA minus small VB is opposite, because it is here VA plus VA minus VB, here it is plus VB minus VA. If you see plus VB minus VA, so it is opposite. So that's why there is a phase of shift of 180. I will visualize it as well for you. I will visualize it as well. Okay, so let's visualize basically. So if I write what is VA, capital VAB, so capital VAB, it is plus VA minus of VB. Minus of VB will be somewhere here. This is minus of VB. So somewhere, right, these two vectors I have to add. So my VAB will lie somewhere around here. Okay, roughly, I'm just discussing roughly. What about small VAB? So it is plus VB minus of VA. Plus VB minus of VA. So this will be minus of VB, VA. This will be minus of VA. Okay, and minus of VA VB, right? So here I will have VB. Okay, so my V small ab will lie somewhere around here, right? V small ab will lie somewhere around here. What are you seeing? If I just club these two phases together, what are you seeing? V capital AB is here, V small ab is here. Previously what did you see? V capital AB is here, V small ab is here. Both are in same phase. Here both are exactly in opposite phase. That's why there is a phase shift of 180 degrees. So that's why there will be a phase shift of 180 degrees. Phase shift of 180 degrees. Okay, so I hope you got the point how it is 180 degrees. Okay, every single thing I have cleared. Now let's discuss about the basically magnitude. Magnitude will not be different, right? Magnitude, like it is magnitude of VAB is magnitude of VA minus VB, which is same, right? Which is same. Magnitude of VAB will be what? So one thing I know, right? I know capital VA is equals to x into, sorry, small VA equals to x into capital VA, right? Or turns ratio. I don't want you to remember this formula, just remember the turns ratio. Simple, like you can derive the formula, right? You can derive the formula. So same thing here, right? VAB and small VAB, it will be root 3 times the phase voltage. This will not difference because there is just a negative sign, that's it. Everything else is same. If I take the magnitude of plus 3 and magnitude of -3, it will be 3 only, right? So here as well, I am taking the magnitude, so it will be root 3 times VAB only. So sorry, it will be root 3 times the phase voltage only. So this will be root 3 times root 3 times phase voltage VA, okay, and this VAB will be root 3 times the phase voltage, okay. Same here, okay, I'm talking about the magnitude, I'm only talking about the magnitude, right? Only talking about the magnitude, I'm not talking about the phase we have already discussed. So the ratio will be same only, so ratio will be same only, that is magnitude of VAB divided by magnitude of small VAB will be same only, that is capital VA upon small VA. So it is x only, capital VA upon small VA is x only, so sorry, it is 1 by x, right? Okay, so it will be 1 by x, whichever one is suitable to you, you can write, like x is anything, right? Like whatever you define, number of turns basically, I mean turns ratio. How you define this turn ratio does not matter. Sometimes it will be k is to 1, it will be 1 is to x, your answer should not change, right? If it is k is to 1, then you will solve according to that. If it is 1 is to x, you will solve according to that. It does not matter, okay. So this was about the star star. So generally, right, star star is never used, star star is never used. Why? Because there are harmonic problems, all those things are there, I will discuss, okay, when we will come to harmonics. Okay, so it is never used, actually never used. Okay, just hold on 1 second, my throat is still hurting, so I will just drink a bit of water. Okay, so this is star star. It is generally it is used for long distance transmission with light loads, okay. It has very poor voltage regulation under unbalanced condition, and it has harmonic problem, harmonics problem. Harmonics problem. So now let's discuss about delta delta transformer. So delta delta, let's first discuss about DD0. So whenever there is phase shift of 0, right, that means the connection diagram in the high voltage and the low voltage will be exactly same, will be ditto same. So here if I see A1 is connected to C2, here also A1 should be connected to C2, here also A2 is connected to B1, so A2 will be B1, B2 will be C1, B2 will be C1, okay. So let me do the connection diagram. So A1 is connected to C2, so A1 is here, that should be connected to C2, okay. Now let's connect my this C1 to B2, right, C1 to B2, C1 B2 will be like this, then B1 will be connected to A2. If I see B1 is connected to A2, same here as well, right, my A1 is connected to C2, so A1 is connected to C2, okay. My B2 is connected to A1, B2 is connected to A1, sorry, B2 is connected to C1, so B2 will be connected to C1, and my A2 will be connected to B1, A2 will be, sorry, A2 will be connected to B1, so A2 will be connected to B1, that's it, okay, that's it, understood, got it. Yeah, so now what are the phase difference? So if I calculate, because phase difference is always with respect to line voltage, and remember the coil voltages will not have any phase difference, so VA will be same as VA, VC will be same as VC, coil voltages. So if I write what is my VAB, so VAB, capital AB, is equals to what, this value, right, this is what it is, plus minus VA, right, plus minus VA, so this will be plus VA. What is V small ab? It is also plus V only, this is plus minus, right, plus minus, this is plus, this is minus, so this will be plus VA only, plus VA only, okay. So angle is 0 plus VA, so basically that means they are in the same phase, right? Why? Because if you see VA is in the same phase, V small a is also in the same phase, that is capital VA is also along capital VAB, so capital VAB will be here in this direction, and small VAB also will be in this direction only, So there is 0 degree of phase difference. That's why it is called as DD0 connection. Okay, what about the turns ratio? What about the voltage ratio basically? So I know VAB is equals to plus VA, VBEB is equals to, sorry, this will be small plus small VA. And what is the relationship between the line and phase voltage for delta? It is same, that I can observe here, right? So basically I know this transformation ratio, that according to this ratio, that my capital VA upon small VA will be 1 upon x. So capital VA is what? VAB. So this will be VAB upon small VAB is equals to 1 upon x. Okay, so my capital VAB equals to basically like this is the turns ratio basically for a delta delta transformer. So it does not, there is no factor of root 3 here. There is no factor of root 3 here. For star star delta delta, there will not be any change in the actual ratio line voltages because no conversion is happening basically. Okay, but we will see in star to delta and delta to star, there will be changes. Let's now come to the second case, that is DD6. So there will be phase shift of what? 180 degrees. Okay, so the circuit diagram is kind of bit wrong actually, because okay, this is, first of all, this should have been, okay, A1 A2 is here only, E2, no, this circuit diagram is correct, the circuit diagram is correct only. So if I see in the high voltage side, my A1 and C2 are connected, but in the low voltage side, C1 and E2 are connected. So connection diagram is completely opposite, and whenever connection diagram will be completely opposite, you will see there will be a phase shift of 180 degrees. Don't worry if you tend to forget all these things, just draw the phasor diagrams, just derive. Okay, so I am explaining you the derivation, that's why. So here my A1 and C2 are connected, so A1 and C2 are connected, so A1 and C2 are connected. Okay, so then I can see that my C1 and B2 are connected, C1 and B2 are connected here. Okay, C1 and B2 are connected, then my B1 and A2 are connected, B1 and E2 are connected here. In the LV side, I see that my A2 and C1 are connected, so A2 is here and C1 is here, so A2 and C1 is connected. Okay, A2 and C1 is connected. A2 and C1 is connected. Then the A1 and B2 are connected. A1 and B2 are connected. So this will be lying somewhere around here. A1 and B2. Then the B1 and C2 are connected. So B1 and C2 are connected over here. Okay. So these are my connections. Now let us actually derive the expression for the line voltages. So if I see what is VAB in the high voltage side, this is plus, this is minus, so it is same, right? It is plus VA only. What about the low voltage side? Low voltage side, this is plus and this is minus. So in the low voltage side, my VAB is minus of small VA. So actually what is happening is that, yeah, there is no phase difference between the coil voltages, but VAB is minus of VA. So my VAB will be lying somewhere around here. Okay, minus of VA and capital VA is here. Okay, so this is my plus VAB will be here. So this is my V small ab and my V capital AB will be in the same phase as the VA. So V capital AB will be in the same phase, that is VA. Okay, now it is obvious, right? It is so obvious that there is a phase difference between the line voltages of 180 degrees. So this is in the top, this is in the bottom. So there is a phase difference. So whenever the connection diagrams are totally opposite, there will be a phase difference, right? So basically what I can comment, is my VAB and V small ab has a phase difference of 180 degrees. That's why it is called as DD6. That is the reason it is called as DD6. Okay, simple to understand. And magnitude is same, right? So magnitude of VAB small ab is equals to VA only, because it does not matter, because it does not matter if I'm taking the magnitude of minus or plus, it will be VA only. Okay, and magnitude of capital VAB will be VA only. Okay, got it? Okay. Okay, yeah. So yeah, that is the case over here basically. So uh, so yeah, so basically if the ratio is like the phase voltage ratio, and the phase voltage ratio is this 1 upon x only, so it will not make any difference. So VAB upon capital VAB will be equals to what? It will be equals to 1 like, sorry, it is x upon 1, so x. So don't remember the formula, just remember the derivation. Okay, so it remains the same, it does not change. Now let's come to a new type of connection, that is delta star. What will happen in delta star actually? So delta star, please make sure that you're following this. Dot is connected with 1 or dot is connected with 2. I'm not telling you this, automatically every diagram it will be mentioned. Okay, if not mentioned, assumption is dot is connected with 1. Okay, great. Now let's discuss about the delta star, right? Delta star will be bit interesting here. Okay, again this will be VAB only. I have to copy this one as well. I'll copy this one as well. Okay, so here what I can do is let's first do the connection diagrams. So A1 is connected to C2 here because it is delta. So this will be delta. So that's why the namings are different. A1 is connected to C2. So A1 will be connected to C2. Okay. Then C1 is connected to B2. Then my B1 is connected to A2. Okay, so these are the connection diagrams. Now let's discuss about the low voltage side. Low voltage C1, A1 and B1 are all okay. One thing is a mistake. Sorry. Here, what is a dot? Dot should have been with 1 only. Okay, sorry. This should have been, actually 1 should have been there outside. Sorry, my bad. So here, right, 1 should be outside, 2 should be inside. So A2, B2, C2 all will be shorted. So A2, B2, C2 all will be shorted basically. And A1, B1, C1 are from where we are taking the output. Okay. Now let's discuss about the line voltages. What is the phase difference between the line voltages? What I observe is, what is VAB? VAB, right? In the high voltage side, it is simply plus, this is plus, this is minus, right? So it is VA, plus minus VA. So this will be basically plus VA only. That is what my VAB is. Okay, what about this? So here, right, what is VAB? So this is plus minus VA, this is minus plus VB. So in this case, my V small ab is plus VA minus VB. So actually there is bit of, like, I know these two are in same phase, but my VAB is actually overall this, right? So it is actually not in the same phase anymore, okay, or 180-degree opposite. So what is this? So I will try to solve it. So I can directly say that VAB, capital AB, will be in the same phase as VA. Okay, so this is the high voltage winding phase sorted. Okay, what about the low voltage winding? So let's solve for the low voltage winding. So for the low voltage winding, where are my phasors? So it is plus VA minus VB. So minus VB will be somewhere here. This will be minus VB, and these two will be added basically. Okay, these two will be added. So okay, sorry, not this. These two will be added basically. So if I add these two, so here this will be V small ab, correct? So I see, of course, there is a phase difference because my line voltage here will lead the phase voltage by 30 degrees. So there will be a phase difference of 30 degree, but the line voltage and the phase voltage in the high voltage side is in the same phase, right? So basically what I can comment is that they are in the same phase. Okay, so if they are in the same phase, that basically means that what is the phase shift? So low voltage winding leads the high voltage winding by 30 degrees. So again, this is also another significance of clock. Okay, clock notation, if you remember, this is also another significance of clock notation. Okay, so what is it? It is 11 o'clock, right? It is coming earlier. So if I draw the clock notation, so my high voltage winding is here and it is coming earlier. Low voltage winding is coming earlier. So it is at 11 o'clock. This is 12. So it will be at 11 o'clock, correct? So they, first of all, there is a phase lead. So my, what I can comment? I can comment that the star side leads the delta side by 30 degrees. Or I can alternatively say that the LV side leads the HV side by 30 degrees. Either way works. Okay, so that's how you will solve this basically. So phase lead is 30. So the naming scheme will be what? It will be dy11 because the delta leads the star, right? And delta is the high voltage, basically high voltage. Okay, sorry, the star leads the delta. So this will be dy11. I have already told you why this will be dy11, because there is a lead of the low voltage by 30 degrees. Okay, what about the turns ratio basically? What will happen to the turns ratio now? So turns ratio, if it is start by delta, does not, I mean, we will discuss. So here, right, what will be the turns ratio? So here, what is the magnitude of VA? Here, magnitude of VAB. It is simply magnitude of VA only, capital VA. Okay, what is the magnitude of VAB here? Small VAB. It will be root 3 into magnitude of small VA. And one relation I know, that my capital VA upon small VA is 1 upon x. So that I will derive. So I know my capital VA upon small VA will be 1 upon x. Okay, so this I know. Okay, I have to find out the ratio of capital VAB upon small VAB. So capital VAB is what? Capital VAB is capital VA only. So this is mod of VA. What is small VAB? Small VAB is root 3 times small VA. So this will be root 3 times small VA. So this ratio is what? This ratio is 1 by x. So my transformation ratio becomes 1 by root through x. I don't want you to remember any formula. Okay, I don't want you to remember any formula. Sorry, my throat is still not up to speed. Okay, so just go by the basics. Go by the basics. Now let's come to another connection, like same delta star but bit differently. So now what we are connecting is, we are connecting this A1 C2 is same here as well. We are connecting A1 C2, so high voltage winding is same only. The low voltage winding we are swapping. Okay, we are swapping A2 and A1. Okay, so A1 is now the common point, so A1 C1 B1 all are common. Okay, so just we are swapping, so basically the phase will be totally shifted again. Okay, so that is what will happen here. So here, right, basically my A1 will be connected to C2, so A1 will be connected to C2, so A1 will be here, that will be connected to C2. Now my C1 will be connected to B2. Okay, C1 will be connected to B2. Now my B1 will be connected to A2, so B1 will be connected to A2. Okay, and here what about this? So here my what I can write is A1, B1 and C1 all are shorted, so these all will be shorted, and my A2 will be connected to B1, right? E2, no, sorry, E2 will not. So this is the star connection. Star connection is very simple, right? So that's it. Now let's discuss about the phase difference. Okay, so again I have to copy this phasor diagram. I'm forgetting to copy this phasor diagram, right? Everywhere we have to copy this actually. So if I observe that this is plus, this is minus, right? This is plus minus VA, right? So line voltage capital VAB is same only, that is plus VA. It does not change, plus capital VA. What about the line voltage small VAB? So line voltage small VAB, I can write here, this will be plus minus VA and this will be plus minus VB. So this VAB, right, is minus of VA plus VB. So it is minus of VA plus VB, or I can write, if I take the negative sign as common, this will be VA minus VB. Okay, so now what we can do is like what I can say is basically what will be the directions here. So I will copy this again, so it will just be the opposite, right? It will just be the opposite, whatever we had calculated previously, it will just be the opposite. Okay, so capital VAB is same direction as VA, but small VAB will be VB minus VA. So I will oppose the VA and I will add these two values, so it will be somewhere around here. Okay, this will be somewhere like roughly it will be somewhere around here. So basically, right, now it will lead the VB by 30 degrees. Okay, so roughly in the clock it will be like my HV winding is here, my LV winding is here. Okay, and it is roughly, this is 6, right? This is 6 o'clock, just the opposite. So this will be roughly 5 o'clock. Okay, roughly, if you want to make a guess. So it will be either 5 or it will never be 4, something like that, right? It will be like 30-degree phase shift. So it will be 5 o'clock. So that's why the connection here is called DY5, because the high voltage winding is delta, low voltage winding is star, so that's why DY, and 5 is the basically the direction of the hand of the low voltage winding hand. Okay, that's why this is 5. Got it? The phase shift, like sorry, the transformation ratio same, right? Nothing is changed. So I can blindly copy this. I can blindly copy this. This will not change, right? This will not change, because it does not matter if I take the magnitude of plus x or minus x, it will be x only, right? That's why, if x is a positive number. Okay, so that's the same thing, because only what has changed, only this value has changed, right? It is negative, so it does not matter if I take the magnitude of a negative number, I will get the same result. So now let's come to another type of connection, and here I will discuss how actually from this connection diagram you can draw the this delta star. That also I will explain. Okay, till now I have not explained that. So if I see here that E2 A1 are here, okay, and like actually not what I meant, okay, नहीं कनेक्शन डायग्राम देंगे ना, वो इधर से ही हो जाएगा कनेक्शन डायग्राम इधर से हो जाएगा. So now let's come to another connection, that is dy1. How is dy1 met? So here if I see that in the primary side b1 and e2 are shorted, so b1 and e2 are shorted like this, then my I guess this a1 and c2 are shorted, so a1 and c2 are sorted, okay. Then b2 and c1 are sorted, b2 and c1 are sorted, okay. So b2 and c1 are sorted. So now what I can discuss is what about the LV side. LV side A1, B1, C1 all are sorted. A1, B1 and C1 all are sorted. Okay, A1, B1, C1 all are sorted. So what I can say is now let's discuss about the line voltages. So here this is my basically what is VAB. VAB here if I see it is minus plus VB, right? So VAB in this case VAB is minus of VB, okay. VAB in this case is minus of VB, and what is small VAB? Small VAB in this case is this is plus minus and this is minus plus, okay. So here, right, it is actually plus VA minus of VB. Now let's discuss about the let's discuss about one thing. What is that thing? That thing is what is the phase difference between capital VAB and small VAB. So I will copy this, paste it over here. So capital VAB will be minus of VB, right? Capital VAB is minus of VB. So minus of VB is here. Minus of VB is here. And my what do you call my what about small VAB? Small VAB is same, right? It is VA minus VB. So V minus VB will be somewhere here. So it will be somewhere here. Now you might have a doubt. What is the doubt? So the doubt might be, are these parallel? No, they are not parallel. Okay. So this is my capital VAB. This is my small VB. These are not parallel actually. So VA minus VB. So the thing is, this angle is 30 degrees. Okay. This angle is 30 degrees. And what is this angle? So if I flip the VB, right, this angle difference is 120. This whole thing will be 180, right? Because I'm just flipping the VB value. So how much will be this angle? This angle will be 60 degrees, correct? This angle is 120. This is a straight line 180. So how much will be this angle? 60, right? 180 minus 120 is 60. So this angle will be 60. Okay. This angle will be 60 degrees. Okay. This angle will be 60 degrees. So what is the phase difference between the high voltage line and the low voltage line voltage? So my high voltage is here, right? This is my basically VAB, correct? Minus of VB basically. So my high voltage is leading the low voltage line voltage by 30 degree. Okay, there are so many times I'm speaking voltage. I hope you are understanding the point. The high voltage is leading the low voltage line by 30 degrees. This is the angle difference, right? This one. This is the angle difference. So from here I can conclude that HV leads LV HV line voltage leads the LV line voltage by 30 degrees. Okay, so how will the clock diagram be? So my HV will always be in the 12 o'clock. So like HV leads. So LV will be in the clockwise direction. So it will be somewhere here, 30 degrees. What is this? This is 1, right? So what is the connection name? Connection name, it is a high, in the high voltage side it is delta. So D, in the low voltage side it is star. So it is Y, and then it is 1. Okay, D by 1. In the high voltage side it is delta, in the low voltage side is Y, so it is D by 1. Okay, that is the answer basically. Okay, I hope you understood the point. So D by 1 will be the answer in this case. Now I want you to solve the case D. Okay, where is the diagram for case D? Okay, diagram for case D is not here. And line voltage, I hope you understand it. What will be the transformation ratio? Again, transformation ratio will be magnitude of VAB divided by magnitude of V small ab. It is what magnitude of VAB is magnitude of minus of VB, which is VB only. Okay, magnitude of VB divided by magnitude of root 3 times the phase voltage. Magnitude of VAB which will be root 3 times the phase voltage. Okay, you can either write magnitude of VA, magnitude of VB, magnitude of VC, all are same. So this will be magnitude of small VB. It is a balanced system. So capital VB upon small VB, so it will be 1 by root 3 x. Don't need to remember the formula, just understand how am I deriving. So what is this capital VB upon small VB? Okay, so here if I see, capital VB is on the HB side and small VB is on the LV side. So capital VB upon small VB, it is 1 by x, simple turns ratio. Okay, so I want you to try this one. This is the last one. I want you to try it by yourself. Okay, so pause the video and try this one by yourself. Like what will be the connections, what will be the group basically, will it be dy11, how it will be dy11, try to prove it to yourself. I want you to do it by yourself, because in the examination hall you have to do it by yourself only, because this circuit diagram will be given to you. You have to draw this, and from there you have to derive the expressions. So do this. So without drawing this vector group as well, I can directly write from here. I will tell that as well, how I can directly solve from here instead of going into the vector group, instead of going into the circuit diagram. I will explain that. Okay, so I hope you have tried. Now I will start. So here if I see E2 and C1 are connected, so E2 and C1 are connected. Okay, so E2 and C1 are connected. Then we have C1 and C2 and B1 are connected, right? C2 and B1. So C2 and B1 are connected. C2 and B1 are connected. Okay, then B2 and A1 are connected. So B2 and A1 are connected. Okay, so these are my connections on the high voltage side. What about the low voltage side? Low voltage side, C1, A1, B1 are all connected, because one is with dot, right? So C1, A1, B1 are all connected together. So it is basically star connection, and the right hand side is from where I take the supplies. So from this diagram as well, you can directly write what is VAB and capital VAB and small VAB. So I will not use this one now. I will use this one. So my capital VAB, right, will be here. If I see, this is plus, this is minus, and this is what? This is simply the phase A voltage, correct? So if I want to write VAB, what will be VAB? Simple this KVL, right? So this will be the AB voltage. AB voltage is coming across this minus plus VA, right? So roughly if I want to show, so this will be my VAB, right? Okay, actually there is no voltage source. Dot. Okay, so so VAB is the voltage source, right? So I can directly write what is VAB, that is equals to minus of VA, right? If I simply apply KVL, because this is dot, so hence this will be minus, so minus of minus VA will be 0, simple KVL. So VAB will be minus VA. What about the right hand side? Right hand side, if I see, this will be plus minus plus minus VA, and this will be plus minus VB, right? So, and this is my again instantaneous polarity. VA will be higher potential, VB will be lower potential. So this will be my VAB. So again, if you apply a KVL in this loop, so this is instantaneous polarity, so this will be plus, this will be minus. Okay, so this will be minus VA plus VB equals to 0. So basically minus VAB minus VA plus VB equals to 0. Okay, so what I can write here is my VAB will be equals to minus VA plus VB. Okay, that is equals to minus of VA minus VB, just the opposite side, right? Just the opposite side. So yeah, so here what we can say is, what we can say is what is VAB? VAB is minus of VA, right? So basically it is here, this is V capital AB, that is minus of VA. And what about this here, right? So here if we see that basically VA minus VB, right? Minus of VA minus VB. So VA minus VB will be somewhere around here. So it is simply VB minus VA. So VB minus VA will be somewhere around here. Okay, it will be somewhere around here. Basically, it will lead the VB by 30 degrees. Okay, and my VA is what? Capital VAB is what? This is small VAB. Capital VAB is here. Okay, so this whole angle is how much? So this whole angle is 180. This whole angle will be 60, right? This whole angle is 120. This whole angle is 120. This whole angle is 180. So this angle will be 60. Okay, so this whole angle will be 60. This whole angle will be 60. Okay, now what will be, so this angle is 30, so how much is this angle? This angle is simply 30 only, because overall it is 60. So what I can notice that again, if I move in the, like, my capital VAB is here, this is my capital VAB. So if I move in the clockwise direction, I'm observing small VAB. So small VAB lags the capital VAB by 30 degrees. So basically what, if my HV is in the 12 o'clock, ignore my drawing. Okay, HV is in the 12 o'clock, so it will lag by will it lag? Okay, no, I'm not going in the, sorry, I'm not going in the clockwise, sorry, I'm going in the anti-clockwise direction. Sorry, I'm going in the anti-clockwise direction. So as I'm moving in the anti-clockwise direction, that means my LV voltage leads by 30 degrees. So I have to move from here, right? I have to move 30 degrees in the anti-clockwise direction. So I will be here. So what is this? This is simply 30 degrees, means this is 1 hour less, that is 11 o'clock, correct? So its high voltage is delta, its low voltage is star, and it is 11 o'clock. Okay, that's how you find out the values. Voltage ratio, like, that's how you find out the notation. And voltage ratio is again very simple, right? Again, it is equals to what? Basically capital VAB divided by small VAB. Okay, so this will be equals to under root, like what is capital VAB? Capital VAB, like magnitude, I'm only comparing the magnitude. So this is magnitude of minus VA divided by magnitude of small VAB. So small VAB is basically what is small VAB? Small VAB is yeah, VA minus VB, right? Magnitude of VA minus VB. So basically it is root 3 into, like this will be magnitude of VA only divided by root 3 into small VA, because line voltage, phase voltage. So what I can say is it is capital VA upon small VA. So capital VA is here and small VA is here. Basically what is the ratio? Capital VA upon small VA, it is 1 by x, right? So this will be actually 1 by x. So this will be 1 by x root 3. Okay, so don't need to remember, just telling how you can understand, right? So I hope all the connections are cleared right now, crystal clear, right? So I hope there is no doubt, and this question will only come. Okay, 3-phase, this will only come, trust me. We will solve the questions in the next lecture. You will see questions are so simple and easy. Okay, you will see that. Okay, now let's come to another kind of connection known as zigzag connection. Okay, because what we wanted is we wanted a connection, like I know my star to star connection has a phase shift of 0. Okay, 0 degree phase shift. My delta to delta connection also has a phase shift of 0 degree, right? This provided either 0 degree or 180 degree, correct? And here as well, either 0 degree or 180 degree. But if I try to do like delta to star, okay, you will always observe there is a phase shift of 30 degree. Okay, if I try to do delta to star, there is always a phase shift of 30 degree, or sorry, star to delta. Or if I do delta to star, right, same thing again, there will be a phase shift of 30 degrees. Okay, there will be a phase shift of 30 degrees. So it's basically maybe we don't want it. Maybe we want a phase shift of 0 only. We don't want phase shift of 30 degrees, right? So we want this feature. So what we do, we modify this design, we modify this star to star to implement a delta to star, okay, that has a phase shift of 0 degrees. Now how will we do it? Okay, how will we do it? We use one connection named as zigzag connection. Zigzag connection. Okay, this is known as the zigzag connection. Okay, we will see exactly how we will do it. So these are actually called zigzag connections. So my primary is star only. The delta side I am actually making few changes. Okay, we will see. We will see how are we actually connecting it. So we actually make two parts of our windings, A, B and C winding, right? Low voltage side. We make two parts. What are the two parts? Like let's this is A1, A2, this is A3, A4. So each of them actually produce voltage of VA by 2. Each of them are producing a voltage of VA by 2. Now I am connecting them differently. Okay, I am connecting the half potentials differently. How am I connecting? So what we are doing is basically, so these are my coils, right? So what we have done till now, we have just changed the, like high voltage side is same, we have just changed the low voltage side. What have you done to low voltage side? What we have done is simply I have just halved the coil. So if I halve the coil, this will be plus VA by 2, this will be plus VA by 2. Here also this will be plus VB by 2, this will be plus VB by 2. Here also this will be plus VC by 2, this will be plus VC by 2. Got it? So just halved the coil. just half the coil, that's it. Okay, now I will connect them in a different manner. I will connect them in a different manner. How will I connect them? So this, right, we will go through this later. Okay, we will see this first. So now what I did is this C3 and C4, I take it out and I connect it here in A3 and A4. Sorry, instead of A3 and A4, and A3 and A4 are connected here, and my B2 and B3 are connected here. So I just swapped the places of the coils. Circuit analysis point of view. Okay, I just swapped the places of the coil. Okay, so 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 now now what I can say is this will be plus minus Va by 2. I know this will be plus minus Va by 2. This will be what? This is plus, right? Dot is with plus. So this will be plus minus Vc by 2. Again, this will be plus minus plus minus Vb by 2. This will be minus plus Va by 2. This will be plus minus Vc by 2, and this will be minus plus Vb by 2. Okay, now how will I solve this? Basically, how will I solve this? So what I can write over here is my Va dash is what? Basically, Va dash, if you see, Va dash is actually subtraction of two values. It is Va by 2 minus of Vc by 2. Okay, and my Vb by 2, Vb dash will be Vb by 2 minus Va by 2. My Vc dash will be Vc by 2 minus of Vb by 2. Okay, these are the values here. So from here actually we will see actually the phase difference, right? We will actually try to find out the phase difference from here. So what is the input phasor? Input phasor is this, right? Input phasor is this. The secondary phasor actually has changed now. The secondary phasor Va dash, Vb dash, all those things has changed now. Okay, so that we have to just be bit careful about that. So this is my primary, this is my high voltage side. High voltage side will not change. Okay, so in the high voltage side, can you tell me what is VAB? So in the high voltage side, still it is star connected. Okay, high voltage side is still star connected. Okay, so if it is star connected, then okay, no, sorry, it is not star connected, it is delta connected. Okay, high voltage side is delta connected. Sorry, high voltage side is delta connected. So if it is delta connected, what will be my VAB? Okay, just normal VAB. Normal VAB will be V only. Assumption is like I'm using the first kind of circuit. So where was in the delta connection, right? Where was it? Where it was VA only. So it was, I guess, no, yeah, here. Yeah, this kind of connection we can do. Delta connection, right? Yeah, this will work. Okay, the secondary I am not drawing. The low voltage side I am not drawing. Just drawing the high voltage side. Okay. Okay, so this is the low voltage side. Low voltage side I will not draw. Okay, so what I can say is this side is fixed, right? This high voltage side is fixed, nothing is changing there. It is delta connected, no problems. What about the low voltage side? What is happening? for the low voltage side. So for the low voltage side, what I observed is, so the right hand side, right, the low voltage winding is basically star connected. Why? Because if I see that this terminal and this terminal and this terminal are all shorted, right, all these are shorted, and the other terminal is just, I'm just taking out the voltage, so it is like a star connection. Okay, like a star connection, I'm saying it is like a star connection, not exactly a star connection. Okay, because these is not the same winding, these are not the same, right, this is A, this is B. Okay, so that's why it is zigzag connection, it is zigzag connection. Okay, so now basically what we can do is, we can connect this, right, uh, connect this somewhere here. So what I can say, VAB is plus V. So what will be V, like what will be V small ab? So it is star connection, so V small ab will be the KVL in this loop, right? I can apply the KVL in this loop. So V small ab will be somewhat like this. V small ab will be somewhat like this, correct? VAB. So this is, if I apply KVL here, this is plus minus V small ab. Okay, plus minus V small ab. So I will apply simple KVL. I will start from here, go throughout this loop, bypass this, then again go throughout this loop and end here, right? Okay, I know you are getting confused with the color. Okay, let me make it green, that would be better. So what am I doing? I'm just starting from here, going throughout this loop here, throughout this loop, covering this, and then here, right? So I should actually not, this loop will be confusing though. Okay, let me do one thing, let me just copy this and paste it in the next page, that will be better. Let me keep it as it is, because otherwise you will get confused. So let me copy this thing and paste it in the next page. Okay, and let me delete these things here, so that will be more clearer to you. Okay, so this is my capital VAB. Small VAB will be what? So small VAB, I will apply the simple KVL, so it will be minus VAB minus small VAB, then plus VA dash minus of VC by 2. So VA dash is what? I will write plus VA dash, and this is what? This is, I'm starting from here, minus VB dash. So I am first encountering the negative sign. Here I was first encountering the positive sign. So that's how I write my KVL. So this will be minus of VB dash equals to simply 0, correct? So VAB will be VA dash minus of VB dash. So what is VA dash? VA dash is simply VA by 2 minus VC by 2. So this will be VA by 2 minus VC by 2. And what about VB dash? VB dash is VB by 2 minus VA by 2. So this will be minus of VB by 2 divided by minus of VA by 2. Okay. So this value will be basically VA by 2. This will be VA, and okay, what we can do, right? VAB and VAC. Should we actually, what I'm thinking is, should we actually do this like this? How will I write these values? Okay, so what we can do, this is what, this is actually VAC, not VAC, sorry, minus of VAC, not minus, sorry, minus of VCA divided by 2 minus of VAB divided by 2. Basically this value is VAB minus VCA divided by 2. Okay, that is what we are calculating here. So how will I find out the values? So it is VAB minus VCA divided by 2. So what is VAB? VAB will be somewhere around here. correct? VAB is somewhere around here, small VAB, right? It is 30 degrees from here, right? This is 30 degrees. What is small VCA? VCA will be basically C, right? Will be somewhere around here. It will lead the VC by 30 degrees. So this will be VCA. Now what we are doing, so this angle is 30 degrees. We are subtracting VCA from VAB. So VAB is here. I will write minus of VCA. Minus of VCA will be here. Okay, this will be minus of VCA. Correct. So what will be the angle? So this whole angle is 180. This angle is 30. Okay. How do I know this angle? This angle, how do I find it out? How do I find this angle out? Okay. Okay. So this angle is if I write this, right, this is minus of VC, right? If I write minus of VC here, this will be minus of VC. So this overall thing is 180 and this is 120. So this will be 60 basically. This whole thing will be 60. So if I write here minus of VC, minus of VC, so I can directly say that this angle will be 60. Okay. So what will be this angle? Because here there is phase difference of 30. Here also there will be phase difference of 30 only. Because VCA again will lead, like minus VCA also will lead VC by 30. So this angle also will be at phase difference of 30. Okay. Now I know this whole angle is 60. This is 30. So this will be how much? This will be 30 again. Okay, this is 30 degrees and this is also 30 degrees. So overall phase difference between VCA and VAB is 30 only. So basically magnitude of both of them are same. So one very interesting point is, if I have two values, let's say this is x, right, and this is x, both are x, two vectors that are x and their phase difference is any value theta. So the resultant will somewhere be in the middle only. Symmetricity, right? I will prove it to you. Don't worry, I will prove it to you as well. It will be symmetric. So this value will be like what is the value? So value will be x cos theta by 2, x cos theta by 2. So it is 2x cos theta by 2 and this degree will be theta by 2. How? Basically, right, if I have two components, here, so this is x, right, and this whole angle is theta. Okay, and obviously it will be like if both are them are x, so automatically the resultant will be in somewhere in the middle. How can I prove it? So if let's say this is the angle bisector, right, so this if this is the angle bisector, so this will be theta by 2. So it will have two components. This will have two components. One will be x into sine theta by 2, other one will be x into cos theta by 2. Okay, and here again I will have, for this vector as well, I will have two components. One will be x into sine theta by 2, other one will be plus x into cos theta by 2. Okay, so this will be 2x cos theta by 2. Okay, okay, so same thing will happen here. So ultimately so this will be the resultant, right, this will be the resultant. So my resultant will be in the middle. So its value will be basically because I'm subtracting, so this is minus VCA only. So what is the magnitude of this vector? Magnitude of this vector is like root 3, like magnitude of VCA, magnitude of minus VCA is what? It is simply root 3 into phase voltage, right? Root 3 into the phase voltage. Let's assume phase voltage as VA only. I'm assuming one voltage VA. Like all the magnitudes are same. Magnitude of VA equals to magnitude of VB equals to magnitude of VC. Okay, and this, right, this will be what? This will be magnitude of VAB. Magnitude of VAB is what? Magnitude of VAB is equals to root 3 into V A only. Okay. Now, so this will be root 3 into, like, magnitude. I will just add the component. So one component will come here, other component will come here. They will cancel each other out, and this component will be added. The middle one, right? Angle bisector. So that component will be in parallel with VA. That component will be in parallel with VA, right? Because this is overall 60. This is 30. This is 30. So obviously it will come in the middle. So that component will be parallel with VA. So this value will be basically root 3. So my, like, magnitude of V small ab, not ab, sorry, it is ab only, right? Yeah, sorry, okay, sorry, this is not ab, right? This is what, okay, so I should have written here VAB dash. Actually that would have been a better representation, otherwise you will get, okay, sorry, my bad. I will write here AB dash, you will get confused. So this is AB dash, okay, this is AB dash. I'm sorry, I'm really sorry, AB dash. Okay, so because you will get confused between this VAB and this VAB dash. I'm sorry. Okay, so this should be VAB dash. Am I correct? No, this should be VAB only. Yeah, the resultant is VAB dash, right? So this will be VAB dash, the resultant. So VAB dash. Okay. So what I can say is, this will be basically root 3 into magnitude of VA into cos of 30, right? Cos of 30. The other component is getting cancelled out. So cos of 30 into 2. Why? Because there are two components. One is this minus VCA, other one is this plus VAB. Both of them has same magnitude. Okay. The cos component will be added. The sine component will be simply subtracted. That will cancel out. Okay. Simple physics, right? Vector law. Vectors, these simple vectors, right? So this will be cos 30 is what? Cos 30 is root 3 by 2. So this will come out to be root 3 into root 3 is 3. So 3 by 2, and already I have a 2 here multiplied. So this value will come out to be 3 into magnitude of VA. Okay, that is what my this value comes out to be. Am I correct here? Okay. This is my VAB. Okay, sorry. Don't forget there is a divide by 2 here as well. There is a divide by 2 here as well, right? So I have to overall, whatever this value comes out, I have to divide this by 2, right? Because this whole thing is what? Basically I am talking about the magnitude. This whole thing, the top numerator is the magnitude. Numerator is the magnitude of this value, right? VAB minus VCA. So it is magnitude of VAB minus VCA. Okay, so 2 will get cancelled out. So this will be basically root 3 by 2 only. This will be 3 by 2. This ratio comes out to be 3 by 2. And what do you notice? Can you tell me what is the phase difference? Can you tell me what is the phase difference between the line voltage and the phase voltage? Now comes the interesting fact. So my VAB dash is here, right? Is in the same phase. VAB dash is in the same phase as VA, because the cos component will be added and the sine component will be cancelled. So cos component will be here only. What is my VAB? What is my capital VAB? So my high voltage was delta connected. It was plus VA only. So can you notice now? Can you tell me the phase difference? The phase difference here is 0 degrees only, right? Because it is also in the top. It is also in the top. VAB dash and VAB are in the same phase. So I can say safely that from the above analysis, from the above analysis, the phase difference between the HV and LV winding is 0 degrees. So that was our actually aim, right? We wanted the phase difference between LV and HV to be 0 degrees. Okay, so that was our purpose, that was our aim. Okay, so we actually got our aim. So basically we can build a DZ because the secondary is Z zigzag, V is 0, or you can also build DZ 6. Okay, just change the polarities, change the terminals, you will be able to flip it. So you will be able to make DZ6. I am not teaching you, but you will be able to do it. Okay, what about the star connections though? So I know that if I go from, if my high voltage is star, what will happen? I know if I go from star to delta, right, there is a phase shift, right? Star to delta, if I go, there is a phase shift of 30 degrees, right? So now if I have high voltage as my star connection and secondary as my, so low voltage as my zigzag, so there will be additional phase difference of 30 degrees, right? Because it has changed from delta to star. So either it will be YZ11 or it will be YZ5. Okay, sorry, not YZ5, sorry, YZ1. Either it will be YZ11 or YZ1, right? Because there is either it will be lagging by 30 degrees or it will be leading by 30 degrees, because star additionally implements a extra 30 degrees phase difference, right? Just like line voltage and phase difference, line voltage and phase voltage, right? Phase difference is 30 degrees, same here, right? So that is the main thing. So I hope you have understood this. One more point, what is the voltage ratio? So what is the voltage ratio? So my voltage ratio now comes out, I will always take the ratio of the line voltages for zigzag. So for I'm deriving for DZ0, for star you can derive further. So for DZ, okay, for DZ it is capital VAB magnitude divided by small VAB. Okay, so this value will be, what is capital VAB? Capital VAB is only plus A, right? Plus A, plus VA. Capital VAB is plus VA. And small VAB. What is small VAB? Small VAB, we have just calculated, it is 3 by 2 of magnitude of VA, right? So magnitude of this divided by 3 by 2 of magnitude of VA only. Okay, sorry, small V, right? Small V. Okay, am I correct here? Okay, this is correct only. 3 by 2 small v. Yes, this is correct. Yes, this is correct. Okay. Okay. So now what I can say is what will be the value basically. So what is capital VA upon small va? Capital V upon small va, this will never change. This will never change. Capital V upon small va will be what? If this is like turns ratio is 1:x, right? 1:x, right? So capital VA is 1, small va will be x. The ratio will be 1/x. So this will come out to be 1/x. Okay, 1/x, like capital V upon small va is 1/x. Another 3 by 2 is already there. So this will be 1/3/2x. So no need to remember this formula. Please draw the circuit diagram and derive, because there are, like, for this, right, the formula will change. Okay, for this the formula will change. What will happen now? The star and line the phase and line voltages will be different, right? Because it is star connected. So here the line voltage, so in this case, right, so that's why I'm not telling you to remember the formula, I'm telling you the derivation. Okay, so here what is happening? So here my, again, it is magnitude of VAB divided by magnitude of V small VAB dash. So sorry, this will be VAB dash, right? Sorry. So what is magnitude of VAB? It will not be plus V anymore, it will be root 3 into VA, because line voltage will be root 3 times the phase voltage. Line voltage will be root 3 times the phase voltage. Okay. So, and this is basically, this is what VAB dash will not change, right? Zigzag, it will not change, it will be 3 by 2 into small VA. Okay, so again VA, capital VA by small VA is 1 by x, root 3 is cancelling out, so it is 1 by root 3 by 2x. So this formula will actually keep on changing, so no need to remember the formula, just understand how am I deriving it. Okay, that is the important portion here. Okay, so I will just summarize few things, that like what are the advantages of zigzag. Provides a neutral point for grounding systems in delta configuration. So even though there is delta, right, delta, the right hand side, it has a grounding configuration. Okay, that is the advantage of zigzag. Provides better harmonic separation, especially third harmonic. So these are few theoretical points. And enhances unbalanced load operation, because the harmonic has been reduced, so it will enhance the load like unbalanced load performance. Basically also to provide 0 degree phase shift, right? Mainly it is used to provide 0 degree phase shift. So zigzag is also used sometimes. Okay, now let's come to the summary, whatever we have learned. So my start to start will provide 0 degree phase shift or 180 degree phase shift, right? So this will be y0 or y6. Okay, so this will be 180. Okay, for delta delta it will be either dd0 or dd6. Delta star, it will be either dy11 or dy5, right? Or dy1, I guess, dy1, if I remember. It was okay, there was dy5 as well, right? If I remember. So I also don't remember, just solve the circuits. dy1 was there and dy5 was also there. Okay, dy5, dy1, everything was there, right? So all kinds of phase differences there, dy1, dy5. So dy1 was there. Okay, dy1, then dy5, and one more was there, right? I guess it was, what was it, dy1, other dy7 was there. No, dy7 was not there actually. dy11, that's it, I guess. Yes, that's it. Okay, like others can also be there, I've just not derived it. Okay, now it will provide always plus 30 degree of phase shift. Start delta, again yd1 is there, yd11 is also there, and others are also there. Okay, delta zigzag, right? Delta zigzag will provide 0 degree for delta zigzag, and this is 30 degree for star zigzag, right? Star zigzag, 30 degree will be provided for star zigzag. Okay, so these are the features. Basically whatever we have discussed, I have summarized everything. Now there is one term known as group table. Okay, transformer vector groups. So transformer vector groups are actually important. Basically it groups the transformers with respect to their phase difference. So basically yy0 dd0 will be here, yy6 dd6 will be 180 degree phase shift. So that is known as group 2. You don't have to remember this, right? Just group the transformers in a same phase shift, that's it. That's simple it. Why? Because it will be helpful in parallel operation. Because I have told you, if there is phase difference between the two secondaries of two transformers, then there will be circulating currents. So that's why if I am connecting two transformers, three phase transformers in parallel, they should be of same group, because they should provide same phase shift from input to output, so that ultimately in the secondary there is no phase difference. That's why this vector group is important. That's why we group our transformers in a vector group. So here I will have yd1 dy1, also yz1 also will be there. Okay, yz1 also will be there, and here as well yy0 dd0 and dz0, right? Dz0 is also there, right? that we just derived at the end. Okay, then we have yy6, dd6 and dz6 is also another option, because whichever one is 0, if I just flip the connections, that will make it 6, right? It will be a phase shift of 180 degrees. So this will be dz6. Okay, then it is yd11, dy11 and yz11 also is a possibility. yz11 also is a possibility. Okay, got it? So plus 30, minus 30, all these are phase differences. I hope you can understand. So these are the conditions, like how to determine the vector group. So basically you just draw the circuit, draw the phasors, whatever method I have followed, just use that and you will be able to find out the group of a particular transformer. That is the most important portion. Okay, so these are few differences actually between star and delta connection. So like we will discuss about this harmonics and all those things in the next to next lecture, so I am skipping these things for now. Okay, harmonics, third harmonics, all those things will be discussed later on. Okay, we will see which ones to prefer. Do I need to prefer delta star or star star or delta delta? We will discuss about this. So I just wanted to add few points about the parallel connection. So we had already discussed this previously as well. These points we had already discussed, right? These 2 points, that essential conditions were for single phase transformer that they must have same voltage ratio, they must have same polarity. These two were the essential conditions. Now in those 2 conditions, if I want my 3 phase transformers also to work in parallel, basically they must have same phase sequence and they must have same phase shift. Phase sequence means if transformer A has ABC phase sequence, transformer B or transformer 1 has ABC phase sequence, transformer 2 also should have ABC phase sequence. Otherwise, of course, it will not work, right? Because the phase difference will be different between A and B. Got it? So they both must have same phase sequence. If they have different phase sequence, this will not work at all, because after A, B will come, then C will come. And if in the second transformer, after A, C comes, B comes, then it is a problem. It is a huge problem. Okay. What about here? What about here? So here they need same phase shift. I've just explained this in the starting itself, right? Basically, if they have different phase shift, so it will have some voltage E angle, let's say minus 30 phase shift. This will be some Z value, and again another transformer will be connected in parallel. Here this will be some Z value, and this will be some angle E angle plus 30. Okay, so this will be ZL. Okay, so already explained, right? There will be a circulating current here. So that's why we discuss about vector group. Vector group actually tells me which provide the same phase shift. So if one transformer is from vector group 2, I have to use another transformer that is from vector group 2 only. I cannot use any other transformer, because they will provide different phase shift, and if phase shift is different, then these angles will be different, then there will be a circulating current. Okay, so that will be a problem. That's why these two are the extra conditions that needs to be satisfied. Okay, so that's basically it for this lecture. I hope you have enjoyed this lecture. We covered the whole 3-phase transformer in a very lucid and very easy manner, right? Trust me, everywhere else they will just bore you with theory. Okay, we have understood the vector groups, how the phase displacement is calculated. I have solved using different methods in different examples. I have solved using different methods. So in the next lecture we will solve all the questions, and trust me, all the questions will come as easy only. Trust me, you will be able to easily crack all the questions. So we will do the assignment solutions in the next lecture. After that we will do harmonics. Okay, we will discuss about harmonics in transformer, and that will end our chapter 1 of transformers. Thank you for watching, and I will see you in the next lecture. Until then, happy learning.